Welcome to the deep dive. Today is July 14th, 2026. And, if you look up right now, the fundamental rules of how humanity interacts with orbit are literally shifting right over your head.
Yeah, they really are. It's a massive transition period.
It is. And we are sitting on this fascinating stack of internal documents and these really detailed engineering infographics. They're breaking down a recent fully successful rocket booster recovery by RSC.
Right, the China Aerospace Science and Technology Corporation.
Exactly. And our mission for this deep dive is to unpack the wild engineering behind this achievement, because it is wild. We're going to explore the brutal economic realities of satellite mega constellations.
Which is really the driving force behind all this hardware,
All right, and we want to understand how catching a falling rocket in the middle of the ocean is rapidly redrawing the global diplomatic map. So to help synthesize this highly technical and geopolitical data, I've got the perfect guide sitting right across from me.
Well, thank you. It's really good to be here. Because what we are looking at in these CASCC documents, it's not just a localized engineering triumph.
No, not at all.
It's essentially a masterclass in how solving a very specific physics problem, like dissipating the kinetic energy of a multi-ton object falling from space, can radically alter the global balance of power and the entire economic structure of low Earth orbit, really.
Totally. And I want to dive straight into the physical reality of this event, just right into the nuts and bolts, because the primary piece of engineering we're looking at, it completely upends the visual language we've come to associate with reusable rocket.
Yeah, it looks entirely different from what we're used to.
Right, because for the last decade, SpaceX has completely dominated this space with the Falcon 9. We all know the imagery, right? The booster comes down, it deploys those 4 landing legs at the very last second, and it touches down upright on the deck of an unmanned drone ship.
Exactly, famously named, Of Course I Still Love You.
Yes. And that whole method is an exercise in supreme rigidity and pinpoint accuracy. It's like a gymnast trying to stick a blindfolded dismount onto a tiny balance beam. But the CSC method, detailed in these new infographics for their Long March booster, it's a complete departure.
A total philosophical shift.
Because there are 0 landing legs. None.
Yeah.
And there is no flat concrete deck. Instead, they've built this massive high-tension net stretched over a structural frame on the deck of a recovery ship. And the booster it flies directly into it. It's like the trapeze artist just letting go and trusting a giant safety net.
It is a profound shift in design philosophy, yeah. In Chinese engineering, there's this guiding principle often summarized as Yukuo Kegang, which essentially translates to softness overcoming hardness.
Softness overcoming hardness. Okay, let's unpack that.
Well, the SpaceX method is a confrontation of hardness, right? You have rigid titanium and carbon fiber landing legs, meaning a very rigid, reinforced steel deck.
Right, metal on metal.
Exactly. And the shock of that impact is immense. Dealing with that shock requires heavy structural reinforcements on the rocket itself.
Which brings up the mass fraction penalty. I was looking at the basic physics here in the documents. Every kilogram of landing leg, every hydraulic actuator you attach to the bottom of that rocket is a kilogram of payload you cannot take to orbit.
You're paying for dead weight.
Yeah. You are essentially paying massive amounts of money just to carry the dead weight of the landing gear all the way up to the edge of space and then all the way back down.
You've identified the core inefficiency of leg-based recovery right there. By introducing a net, the softness, KSC fundamentally changes the physics of deceleration at the exact moment of capture.
It's just not a sudden stop.
Right. Instead of a near instantaneous transfer of kinetic energy into rigid legs, the net stretches. It increases the duration of the deceleration, which dramatically lowers the peak G-forces exerted on the rocket's airframe.
Oh, that makes sense.
Yeah, because the external environment is absorbing the shock, CSC could essentially strip all that structural weight off the rocket, converting it directly into payload capacity.
But wait, taking off the landing legs doesn't just change the weight. It completely rewrites the guidance parameters, doesn't it?
Oh, absolutely.
Because if you were landing on a flat deck, you have to hit a highly specific X, perfectly vertical, with 0 lateral momentum, or the whole thing tips over and explodes.
Which we've seen happen many times.
Right. But a net acts like a funnel. You don't have to hit a 10-centimeter target. You just have to get the rocket into the general volume of this massive net, and the tension of the cables does the rest of the stabilizing work for you?
It widens the margin of error for the terminal guidance system significantly. However,
Yeah.
you cannot ignore the immense material science challenges this introduces.
Yeah, I was wondering about that.
I mean, this isn't a circus act. The lower fuselage and the engine bells of that rocket have just experienced atmospheric reentry. They are radiating intense thermal energy.
They are literally glowing hot.
Exactly. So the net material has to withstand not just the kinetic impact of a multi-ton vehicle moving at a residual velocity, but it has to catch this blazing cylinder without the fibers melting or degrading under extreme heat.
Okay, but I have to push back on the operational side of this, though.
Yeah.
Because catching it in a heat-resistant net sounds elegant on paper, but getting it out seems almost, well, it seems blunt, like a logistical nightmare.
It's definitely the tricky part.
Because the infographics briefly touch on the turnaround process, and it looks incredibly messy. With a Falcon 9, it lands, they weld it to the deck, and a crane just picks it up by the hard points when they get back to port. Nice and clean.
Right.
But with this KSC method, you have a rocket tangled in high-tension cables on a moving ship. You have delicate fluid lines, avionic sensors and attitude control thrusters covering the exterior of that booster. How do you extract it without crushing the very hardware you were trying to save?
The extraction process is undeniably the Achilles heel of this method right now. Yeah. The CSC documents acknowledge that removing a multi-ton booster from a high-tension capture system on a rolling sea, it introduces high risk of secondary damage.
I can imagine.
Furthermore, you can't simply reset the net. Every single cable, every node must be rigorously inspected for micro tears, thermal degradation, or stress fractures before it can be trusted with another falling rocket. So the turnaround process is labor-intensive and highly complex.
Wow. So they essentially traded the complex engineering of landing legs for the complex operations of a maritime extraction team.
That's a good way to put it.
They simplified the rocket, but massively complicated the ocean cruise job. But let's rewind the tape a bit, because understanding the net is really only half the equation. The choreography required to get the rocket from the edge of space down into that net is wild.
And the flight sequence is incredibly demanding.
I want to look specifically at the engine they're using, the YF-100K, because it seems like the bedrock of this whole maneuver.
It absolutely is. The YF-100K is a liquid oxygen and kerosene engine. It uses a staged combustion cycle, which is, frankly, a massive upgrade over their legacy hypergolic engines.
Right.
And for this specific mission profile, its most critical feature is its multi-restart capability under extreme aerodynamic loads.
Right, because when the booster separates from the second stage, it's essentially in a vacuum, falling backwards at supersonic speed.
Exactly. Head forward, engines back.
I was reading through the telemetry data in the source, and to actually slow down, they have to reignite that YF-100K engine while basically plowing through the upper atmosphere. But in zero gravity, or in a free fall state, the liquid fuel isn't just sitting nicely at the bottom of the tanks, right?
No, it's not.
It's floating around in globs. If you just spark the engine, the turbopumps will suck in a mixture of gas and liquid, overspin, and essentially shred themselves to pieces.
You're describing the ullage problem, and it's a massive hurdle in rocket recovery.
The ullage problem.
Yeah. Before they can ignite the main engine to slam on the brakes, they have to fire cold gas thrusters to push the entire vehicle forward just enough to force the liquid oxygen and kerosene to settle at the bottom of the tanks right over the intake valves.
So they have to create artificial gravity for a few seconds just to organize the fuel. That is so cool.
It is, and they have to do this while the vehicle is experiencing immense dynamic pressure from the atmosphere. They reignite the YF-100K in a literal hurricane of plasma.
Wow.
The thrust pushes against the direction of travel, rapidly bleeding off velocity. It takes the booster from supersonic down to a subsonic regime where the grid fins and the attitude control systems can bite into the thicker air and physically steer the vehicle toward the recovery zone.
Which brings us to the detail in this document that absolutely blew my
A
mind.
moving ship.
Yes. The recovery zone isn't a fixed point. SpaceX uses an autonomous spaceport drone ship. It's essentially a massive barge that uses thrusters to hold a single GPS coordinate. It actively fights the waves to stay completely still.
Right, a passive catcher, essentially.
But Casey's recovery ship is an active, powered naval vessel. It doesn't just sit there. It drives through the water, adjusting its heading and speed to physically catch the rocket. Here's where it gets really interesting to me. If the ship is moving to catch the rocket, doesn't that make the math infinitely harder?
It adds incredible complexity, yes.
I mean, you have two highly dynamic, moving targets trying to meet in the ocean. You have to account for wind shear on the rocket and the ocean current heave, pitch, and roll on the ship. Why would you want the ship to be moving?
Because a large naval vessel actively under power, cutting through the waves, is vastly more stable than a flat-bottomed barge just bobbing on the surface.
Oh, I see.
By maintaining forward momentum, the ship can turn directly into the wind and the swells, which stabilizes its roll. The ship's active maneuvering essentially absorbs the environmental unpredictability at sea level, allowing the rocket to fly a slightly more generalized trajectory. The ship acts as the final microadjustment.
That makes a ton of sense. It's the difference between an outfielder actively tracking and running under a fly ball versus standing completely still and hoping the wind blows the ball perfectly into their glove.
Exactly. It's a great analogy.
The active movement actually gives you better odds of making the catch. But the margin for error on the rocket's descent timing is still terrifying.
Oh, absolutely.
The source data highlights the terminal reentry ignition timing as the most sensitive variable in this whole thing.
Because if the flight computers ignite the YF-100K even a fraction of a second too early, the engine burns too much fuel high up in the atmosphere.
And then what happens?
The rocket slows down, sure, but then it runs out of propellant before it reaches the ship, essentially turning into a multi-ton, unguided bomb plummeting into the ocean.
Yikes. And if they ignite it a fraction of a second too late?
The vehicle doesn't shed enough velocity. The aerodynamic forces tear the airframe apart, or it punches straight through the aramid net, the steel frame, and the hull of the recovery ship.
So the mathematical precision required is just absolute.
It is absolute, and this is where the context of this achievement is vital. SpaceX went through an incredibly public, incredibly destructive trial and error phase.
Right. We all remember the blooper reels.
Dozens of rockets exploding on the deck or crashing into the sea before they dialed in that timing. The fact that SACE executed this active ship net catch maneuver successfully on their very first attempt is indicative of massive advancements in their fluid dynamics modeling and simulation software.
That's a really huge point. They didn't have to blow up 20 rockets to figure it out because they could simulate the physics accurately enough to nail it on day one.
Exactly.
But the source material is also very clear about this. A sample size of 1 is just a proof of concept.
Right, it doesn't prove industrial reliability.
Yeah, it shows it's physically possible, but the real test is the reuse attempt scheduled for the end of 2026, extracting it, inspecting that net, checking the rocket, and firing it again.
And that transition from a single successful test to a reliable operational cadence brings us to a fundamental divergence in how these two aerospace giants approach engineering.
I want to spend some time on this because the documents make a huge point of clarifying that this isn't just like a legacy Long March 2 or Long March 5 rocket that they decided to bolt some grid fins onto.
No, not at all.
This booster is a specific configuration of the new generation Long March 10. They designed this vehicle from a blank sheet of paper with the explicit requirement of reusability.
The distinction between built-in reusability and bolted-on reusability dictates the entire development life cycle of an aerospace program.
It's like designing a house.
Yeah.
If you know you want a massive underground garage, you draw it into the initial blueprints. You pour the foundation deeper, you route the plumbing around it, you integrate the structural supports.
Which takes a lot of time.
Right, that's the CSE approach. It takes years of planning before you ever break ground. But the SpaceX approach with the Falcon 9 was like buying an existing house, deciding you want a garage 5 years later, and trying to excavate a basement underneath a structure that is already fully built.
The excavation analogy perfectly captures the engineering debt SpaceX took on.
You can do it,
Yeah.
but you have to make all these weird structural compromises, right? Things are going to crack along the way.
Precisely. The original Falcon 9 was designed to be expendable. When they decided to make it reusable, they had to retrofit the landing legs, the grid fins, and the extra propellant tanks onto an airframe that wasn't natively optimized for those loads.
Right.
This iterative approach, building, flying, braking, and fixing, allowed SpaceX to move incredibly fast. They generated real-world flight data instead of just relying on lab simulations.
But the downside is a chaotic evolutionary path.
Yeah,
You end up with a vehicle that carries the scars of its own development.
exactly. Kara C, conversely, chose the ground-up approach. This requires a brutally long R&D cycle. You are stuck in the laboratory for years.
Just doing math.
Right, accounting for the thermal stresses of reentry and the kinetic shock of a net capture in every single weld and every line of code before the first vehicle ever reaches the launch pad. But the payoff is graceful redundancy.
So the final vehicle is highly integrated and structurally optimized.
Yes. They looked at SpaceX's public trial and error phase, absorbed the lessons about hypersonic retropropulsion, and applied it to a clean sheet design. Saosi has a massive engineering bench and decades of Long March heritage to draw on.
And the implication of the source data is that because of this built-in philosophy, once Satorasi fully validates the net catch system, their scaling speed is going to shock the world.
They won't be tinkering with the design, they will just start mass producing them.
Which pivots our analysis from the physics of rockets to the economics of space.
The brutal economics.
Yeah, because let's be real, no nation spends decades and billions of dollars developing a giant net and a reusable rocket architecture just to prove a point. The engineering is totally subservient to the economic math of the next era of orbital infrastructure.
And the numbers in these documents are staggering.
They really are. Let's look at the baseline cost reduction that SpaceX forced onto the industry. Before reusability, a single Falcon 9 launch cost roughly $67 million.
Which is astronomical.
You build a massive, complex machine. You use it for 9 minutes and you throw it in the ocean. But by recovering the booster and reusing it, the marginal cost of a launch plummeted to roughly $15 million.
A nearly 80% reduction in overhead.
Wow.
It is a financial earthquake that fundamentally altered the barrier to entry for space access.
And this cost drop collided with another massive shift. According to the infographics, the cost of manufacturing satellites, specifically the small form factor satellites used in internet constellations, has also cratered.
The industrialization of the payload itself.
Yeah, we used to build bespoke, school bus-sized satellites that cost $1 billion and took 10 years to construct. Now, companies are churning out flat-pack satellites on assembly lines for just a few $100,000 apiece.
So you now have cheap satellites ready to fly. But the source material makes a crucial mathematical argument here, which is that mass-producing cheap satellites means nothing if the delivery mechanism remains expendable.
Right. So what does this all mean for you, the listener?
Right.
We hear about tech billionaires saving a few million bucks on a launch. Does dropping the price from 67 to 15 million really change human history, or is it just corporate accounting?
Oh, it changes everything. It's not just about saving money. It's about unlocking an entirely new business model. The mega constellation.
Okay, walk me through that.
Well, if you want to build a mega constellation of, say, 10,000 satellites to blanket the Earth in broadband internet, and your rocket costs $67 million and gets thrown away every time, the math simply collapses.
Right.
Even if the satellites are free, the launch costs alone would bankrupt any corporate entity or nation-state trying to deploy it. You cannot build a continent-spanning highway network if you have to destroy the dump trucks every time they deliver a load of asphalt.
That is a great visual.
Reusability is the singular variable that unlocks the door to low Earth orbit commercialization. Reusing a booster 10 times slices the launch cost to a tenth. By dropping the launch cost to $15 million or lower, you transform low Earth orbit from a boutique elite scientific domain into a mass-scale commercial utility.
It acts as orbital mass transit.
Exactly.
Which sets the stage for the massive rivalry detailed in our source material. Because this economic reality isn't happening in a vacuum. It is fueling a direct head-to-head battle between two massive satellite networks, SpaceX's Starlink and China's Guoang.
And the translation of Guoang is literally national network.
National network, right.
Understanding this rivalry requires looking at how engineering achievements translate into geopolitical leverage.
Let's run the numbers as of today, July 2026. Because looking at these numbers, Starlink has a colossal head start. They have roughly 6,000 satellites currently operational in orbit, providing high-speed internet to over 4 million active users globally.
They've proven the market.
They've built the user terminals and established the operational cadence. Now, in the other corner is Guoang. Their master plan calls for 13,000 LEO satellites occupying orbital bands between 500 and 1,100 kilometers altitude.
But currently,
the source notes, they only have a few dozen experimental satellites actually up there, having just started deployment in 2025. 6,000 to a few dozen. Is Guoang just hopelessly behind, or is there a variable here we are missing?
looking purely at the current orbital assets, the disparity is massive, yes. But the source data clearly warns against writing Guoang off as hopelessly behind.
Why is that?
Because China's massive advantage is highly centralized policy and funding. When a project is designated as a national strategic imperative by the Chinese state, the funding mechanisms operate entirely differently than a private company navigating capital market.
Right, state treasury opens.
Exactly. But beyond the money, look at the logistical infrastructure detailed in the report. In 2025, China executed nearly 70 orbital launches.
70 launches in a single year. They surpassed the U.S.
And they did it almost entirely with expendable single-use rockets. That is the critical metric. It proves that the industrial base, the supply chains, the launch pad turnaround times, and the operational teams are already humming at an elite industrialized capacity.
Their infrastructure and cadence are already there.
Yes, they have the massive highway infrastructure built. They were just driving expensive single-use vehicles on it.
So if you connect the dots,
Yeah.
they have the state funding, they have the mass production satellite factories, they already have a 70 launch per year pad infrastructure. And now, thanks to this net-catching breakthrough, CSC has proven reusability. They have shattered the final cost barrier.
The analysis here isn't just that Guam will slowly catch up. It's that with reusability unlocked, the deployment speed we are about to witness will likely be unprecedented.
They are going to flood low Earth orbit.
And this rapid expansion instantly elevates this from a commercial competition over internet subscribers into a hard-power geopolitical conflict. The competition isn't just commercial. It dictates global power.
Which moves us from orbits right down to international relations. The source quotes Victoria Sampson at the Secure World Foundation, who calls this reusable capability a game-changing move.
It absolutely is.
And the document goes deep into the weeds on how low-cost launches can be utilized as a potent diplomatic tool. We have to look at the global space market, which is deeply bifurcated right now.
Much of that bifurcation stems from U.S. national security rules, specifically ITAR regulations, the International Traffic in Arms regulations.
Because space launch tech is basically missile tech, right?
Inextricably linked to ballistic missile technology, yes. So the U.S. heavily restricts the export of any satellite or component containing American tech. If a satellite has a single American microchip in it, it generally cannot be launched on a Chinese rocket.
Which essentially split the world into two mutually exclusive camps.
Yeah.
The U.S. and Europe on one side and China and Russia on the other.
But the dynamic of those sectors is changing, largely driven by what happened on the ground in Ukraine.
Oh, this is a huge point in the documents.
The source material references a recent leak from investigative journalists revealing that China and Russia are actively collaborating on research to disrupt Starlink.
Now, obviously, we're just reporting what's in the source material here. We're not taking any political sides.
Yeah.
But we need to look at this purely through the lens of strategic reality, as outlined in the leak.
Exactly. The conflict in Ukraine demonstrated unequivocally that a commercial low Earth orbit satellite internet constellation provides an incredibly resilient tactical advantage in a war zone.
Because traditional communication nodes like cell towers, fiber optic hubs, those are static targets easily destroyed by artillery.
But thousands of constantly moving satellites are nearly impossible to degrade effectively. It provides high bandwidth, unjammable command and control right to the front lines.
So from the perspective of rival nations, Starlink's effectiveness essentially forced them to view commercial satellite internet as a vital national security threat.
Precisely. It fundamentally raised the stakes for the Goong rollout. Goong isn't being built just to stream movies, right? It is being built to establish a sovereign, undisruptible, strategic communications network that is entirely immune to Western sanctions or interference.
And imagine being a non-aligned country right now. Say you are a developing economy in South America, Africa, or Southeast Asia. You desperately need orbital infrastructure, weather monitoring, agricultural observation, or just rural broadband.
Which is critical for economic growth.
Historically, accessing space was prohibitively expensive, and you were at the mercy of U.S. or European pricing. But now, if you're a nation caught in the middle just wanting to put a weather satellite up, this net-catching rocket suddenly gives you a whole new menu of diplomatic options, doesn't it?
Subsidized access to orbit is the ultimate geopolitical leverage in the 21st century.
How so?
Well, by offering cheap, reliable access to space, China can draw unaligned nations into its technological ecosystem. If China can offer a developing nation a turnkey solution, we will build your satellite, launch it on our cheap reusable rockets, and manage the data on our ground stations, it draws that nation deeply into their sphere.
You essentially trade launch access for strategic alignment.
Yep.
You get cheap internet for your country, but you are now locked into Chinese data protocols, hardware, and influence.
Yes. Catching a rocket in a net over the ocean translates directly into winning a diplomatic ally in the global south. It is an incredible web of causality.
It really is. And to fully appreciate this moment, we need to zoom out and look at the rest of the board right now, as of July 2026.
The transition period is chaotic.
Infographic O5 provides a global scorecard, and it paints a picture of extreme volatility. Let's look at the competitors. First up, Blue Origin. According to the data, they successfully recovered their massive new Glenn rocket booster in 2025, and they actually reused it in April of 2026, a huge milestone. But then, a month later in May, they suffered a mysterious launch pad explosion.
It reset their progress completely.
Total loss. Their progress is completely grounded while they investigate.
It perfectly illustrates the fragility of this transitional phase. Mastering the physics of descent is only step one. Mastering the complex plumbing and fluid dynamics of rapid turnaround is where catastrophic anomalies often hide.
One valve failure can erase years of momentum.
Absolutely.
Then you have Rocket Lab pushing forward with their Neutron vehicle, and Stoke Space, which the source highlights as planning a test of a fully reusable rocket by the end of 2026.
Stoke Space is a fascinating contrast to the CSC Netcatch. Case SC is recovering just the first stage booster. Stoke is attempting to recover the second stage from orbital velocities.
Oh, wow.
Yeah, utilizing a novel Hydrolox Aerospike engine and an active regenerative heat shield. The diversity of engineering solutions currently being tested is staggering.
And finally, you have the incumbent, SpaceX. The scorecard notes that the Falcon 9 continues to break reuse records. It's practically carrying NASA and the Space Force on its back.
But their next-generation vehicle, Starship, is struggling.
Right. The source describes their May 2026 test as mixed, and the newly listed corporate entity, SpaceX Group, is planning a critical test this month, July 2026. The booster static fire looks fine, but the real test is ahead.
When you synthesize the scorecard, the narrative is clear. It sounds like the era where SpaceX was the only player in town is officially over.
We've got nets in the ocean, pad explosions, and new companies testing full reuse all in the same year.
It proves that reusability is no longer a proprietary SpaceX magic trick, It is the baseline requirement for the new space age.
If your aerospace company is still drafting expendable rockets in 2026, your product is economically obsolete before the blueprints are even finished.
Exactly. The transition period is explosive, but the technology is irrevocably spreading.
We have covered an immense amount of ground today. We started by dissecting the brilliant, counterintuitive engineering of softness overcoming hardness, where a giant net replaces heavy landing legs.
It's a total paradigm shift.
We traced how that single physics solution drops launch costs, unlocking the mass transit economics required to build 13,000 satellite mega constellations. And we followed that economic reality straight into a deeply divided geopolitical space race.
Where low-cost rockets are deployed as diplomatic leverage.
Right. But before we wrap up this deep dive, I want to leave you, the listener, with one final provocative thought to mull over. Something building purely on the source's data regarding these LEO constellations.
It's an important point.
Look back at the orbital parameters from Infographic 06. Guowang is planning 13,000 satellites in the orbital band between 500 and 1,100 kilometers. Starlink currently operates 6,000 satellites in that exact same low Earth orbit band.
The physical volume of that specific orbital shell is finite.
Exactly. Thanks to reusable rockets, launch costs, the ultimate barrier to space, are vanishing. But as China and the U.S. prepare to pack nearly 20,000 active, moving satellites into the exact same narrow bands of orbit, the ultimate bottleneck is no longer gravity.
No, it's not.
And it's no longer money. It's orbital real estate. When you factor in the explicit mention of nations researching how to disrupt these networks, the potential for friction is immense.
It's a crowded sky.
The question you have to ask yourself isn't who can build the best rocket anymore. The question is, what happens when these two massive rival networks physically run out of room to share the same sky?
That is the defining strategic dilemma of the next decade.
It's going to be wild to watch unfold. Thank you so much for joining us for this deep dive. Keep looking up, keep asking questions, and we'll catch you on the next one.